Hi there. My name is Sridhar, and I'll be talking about correlated randomly growing graphs. This is joint work with Miklos Ras, who is in the Orphy department at Princeton University. And thank you to IMS for organizing this great symposium. So the purpose of randomly growing graphs is to model the way networks form over time. To help gain some intuition about them, I'll illustrate how to construct a uniform attachment tree, which is the simplest model of a randomly growing graph. We initialize the growth with a seed graph S. Using this as a base, we're going to build larger and larger graphs by adding new vertices and edges sequentially. When we add a new vertex, it chooses an existing vertex uniformly at random and attaches an edge to it. We can iterate this process again and again to form networks of arbitrary size. You can imagine that there's other possibilities for the growth rule. One common one that's often used in models of social networks is called preferential attachment, where the probability of connecting to an existing vertex is proportional to the degree of that target vertex. More generally, we can represent any randomly growing graph by the following schematic. Starting from some seed graph S, we add vertices and edges according to some growth rule to eventually generate large networks with n nodes. Mickey and I came up with a new model of correlated growing graphs. And here's how it works. We start off with some seed graph S, and we grow it until it has T star vertices. At this point, the growth splits into two independent copies to produce GN1 and GN2. GN1 and GN2 are going to have some shared structure, which is induced by this shared subgraph S star. At the same time, the marginal distributions of the two graphs are identical. They're both grown from the same seed graph via the same growth rule into GN1 and GN2. Now, there are two statistical questions that come out of this quite naturally. Given only the graphs GN1 and GN2, can we detect correlated structure? And can we estimate properties of the correlated structure? Our inspiration for studying this model came from the graph matching problem. In this problem, the goal is to label vertices of two networks in a way that minimizes the dissimilarity between the two networks. For instance, one might want to minimize the number of disagreeing edges. This problem has many applications in diverse domains, but unfortunately it's NP hard, even to approximate. This has motivated the study of graph matching for probabilistic generative models in order to capture average case rather than worst case instances. Because the Erdős-Rényi model is the simplest and most widely studied random graph model, a lot of the prior literature has studied correlated Erdős-Rényi graphs. However, Erdős-Rényi graphs don't capture many properties of real-world networks, such as the dynamic manner in which they form. Our hope is that in studying correlation in randomly growing graphs, we can design algorithms for measuring correlation in networks that work well in practice. All right, so coming back to our study of correlation in randomly growing graphs, we'll first address the problem of detecting correlation in a pair of graphs. This can be phrased as a hypothesis testing problem. In the null hypothesis, the two graphs are independent, and in the alternative, the two graphs are correlated. The natural thing to look at is the total variation between these two distributions. The total variation is going to be positive if and only if we can find a hypothesis test that can distinguish between these two hypotheses. This leads us to our first main result, which establishes general conditions under which detection is possible with positive power. We consider a large class of growth rules too that fit that are so-called Markov. Now, the first interesting thing in this theorem is that it holds for any T star greater than the size of the seed. What this means is that detection is possible even if the two graphs are grown together for a single time step, which is the minimal amount of correlation one could imagine. The key enabler for this result is this condition right here, which I call the seed has influence. What it means on a high level is that if you initialize a growth process with two different seeds, the two networks that grow from these two different seeds are going to look different. To kind of see this more concretely, here I have two preferential attachment trees that have been initialized with two different seeds. On the left, the graph has been initialized with the star, and on the right, the graph has been initialized with the path. Now, even though the number of vertices in each of these graphs is much larger than the size of the seed, we can see that the structure of the seed has heavily influenced the way in which these trees grow. And this is what I mean by the seed has influence. Now, this phenomenon is not unique to preferential attachment. Several authors have studied this phenomenon both in preferential attachment as well as uniform attachment. And it's conjectured that this phenomenon holds more broadly in many more classes of randomly growing graphs. So now, if we combine this rich literature on the influence of the seed with our generic detection result, we get the following corollary. In uniform attachment and preferential attachment trees, we can detect correlation even if the two graphs are grown together for just a single time step, which is quite remarkable. Now, this leads to a natural follow-up question. Here we have detection with positive power, but when can we get detection with high probability, or in other words, detection with power 1? The next theorem shows that as the amount of correlation T star grows large, the total variation distance between the two distributions tends to 1. As long as we can find some magic function f, such that f of gn converges to some absolutely continuous random variable. This condition is somewhat vague and mysterious, but for the moment, let's assume that it holds. Then the proof of the theorem is quite intuitive. It essentially suffices to look at the absolute difference between f of gn1 and f of gn2. If the two graphs are independent, then f of gn1 and f of gn2 are independent random variables that are absolutely continuous. Hence, we expect that they wouldn't be too close to each other. On the other hand, if the amount of correlation is quite large, we would expect that f of gn1 and f of gn2 are quite close to each other. So by just comparing the probability under these two different distributions, we see that the total variation is quite close to 1 when the amount of correlation is large. We can make these ideas a bit more concrete in the case of uniform attachment and preferential attachment by computing a specific statistic f. To do this, we'll use notions of centrality in trees. So first, we define the anti-centrality of a vertex v as follows. We root the tree at a vertex v, and then we find the largest subtree of that vertex. The anti-centrality is the size of this largest subtree, which is highlighted in orange. The centroid is the vertex with the minimum anti-centrality. It turns out that if you normalize the anti-centrality of the centroid, this ends up converging to an absolutely continuous random variable, which is exactly what we needed. In other words, the anti-centrality of the centroid is a statistic that will allow us to detect correlation with power tending to 1. Now that we've solved the questions of detection, we now turn to questions of estimation. In this theorem, we show that the correlation time T star can be estimated with vanishing relative error as the amount of correlation grows large. On a high level, the construction of the estimator is all about matching the centroids in the two trees, as well as subtrees of the centroid. Well, we're first going to match the largest subtrees of the centroid, which are highlighted in orange. It turns out that the squared difference between the normalized subtree sizes is on the order of 1 over T star. So to get an estimator for T star, we just invert this quantity. It turns out that this gives us a coarse estimate. Our estimator is close to T star within logarithmic factors. To make this more refined, we're going to have to match many more subtrees of the centroid and compute similar subtree difference statistics. When we average over many of these, we reduce the variance to a point where we can get vanishing relative error. Okay, that concludes my talk. Thank you for listening. For more information, you can check out my archive link. I also have a poster on this same paper, and I will be at the live discussion session on random graphs, which is Thursday from 1 p.m. to 3 p.m. UTC. Thank you again.